Good morning. You're welcome to the class.
Morning. Good morning.
Good morning.
Yeah, I'm having issues. I can't share my screen, so just give me a few minutes and then I see what to do. I don't know why I can't share my screen. Okay, so now I'm able to share. So in the meantime, I think we need to be discussing we need to set dates for our cut. Oh, I see everyone has come in, which is good. Okay, but we can take these few minutes to discuss the first cut that we're going to be having. I'm thinking we should have our first cut in the first week of November, which is about 2 weeks from now. I think we can still have it on Wednesday. Let me see. I hope I'm not talking to myself. Okay, let me just share my screen for a short time and let me know if the video is disturbing you. Let me just share a video so that you can see me for a short time as we discuss. Yeah, so we need to set the time for our cards. And I'm thinking of 2 weeks from now, which is basically on Wednesday. I don't know which date will that be. Let's see which date will it be. Which date will it be? Just a minute. Wednesday next week will be, 2 weeks from now. Wednesday, 2 weeks from now, it will be the 1st of December. So I'm thinking we should have our first cut on the 1st of December. So let me see who thinks we shouldn't, because the answer, my default is that we are all agreeing, but I might be wrong. Okay. So who thinks we should what? Who thinks otherwise? Who thinks otherwise? I can see someone has reacted. That's okay. So Nampanji is saying it's okay. Emmanuel Victor is saying it's okay. Okay, so if I have 2 votes who says it's okay, so are there any other people who think we shouldn't have it? So, of course, if you keep quiet, it means that you are consenting. Silence means consent. Okay. So if you are not objecting, then it means we can have our first cut 2 weeks from now. Okay, that's good. So, and it should be physical, I think, since now we can meet at the university, we should be able to have a physical one. In our normal class, we're supposed to have, in the normal class, we're supposed to do 2 weeks from now, the exams will be done. Yes, so therefore we can be able to sit there. Okay, but I don't see Ababu in the call. I don't know who's going to be our class representative for today to communicate to the rest of the people. Let me see. Okay, let me pick on the ones who answered. Emmanuel Victor, can you be our class representative for today? Please speak. You can unmute yourself and make a comment. Victor, unmute yourself and make a comment.
Okay, there's no problem. I can be.
Okay, so we are going to have our first cut on the 1st of November, and it's going to be physical. It will cover everything that we have done, including the things that we're going to be doing this week. Now, I'm very sorry that I missed last week. I was given extra assignment by the university and it required me to physically be there, so I could not actually excuse myself to come for the lecture. But I talked to Ababu and he said that you have given me that slot of on Friday from 8 to 10. I am trying to organize a link for that time. Hopefully it shall continue being sorry, it shall be exactly from 8 to 10, but I'm not so sure, just in case someone has taken the slot, we may have to reschedule, but I'll let you know by the end of the day. I'll let you know by the end of the day. So basically it means that we're going to have class on Friday. So tentatively, we're going to be having class on Friday. Okay. Yeah, so we're going to be having class on Friday, so we can also book that. Okay, so I think we are ready to start. We are quite a number now. We are about 20 people in the call, which is good. Because I see you're 22, but since I have 2 gadgets, that means we are 20. So we'll be able to start. Any issues so far? Can I, just before I dive into our new topic today, any issues? Again, Victor, I will ask you to comment. Are there any concerns or issues that people are having with the lecture that we are having? I mean, so far we have had several lectures, so it would be nice to hear. Nampanji, let's get an opinion from Nampanji. The lecture recordings could not play because of the subscription. Oh yes, I think there was something like that. But if you try playing them now, please try playing them now. I think they should be able to play because yes, there were some issues of licensing, but it looks like it has been sorted. There were some issues of license that's been sorted. Try playing them now, and if you are not able to play them, please communicate to Victor, since he's our class representative for today, or Ababu, so that we can rectify that. Okay. Okay. Any other issue as far as this lecture is concerned? Any other issue? Thanks, Claire, for the comments. Any other issue? And Ampanji, can you unmute yourself and and make a comment if there are any issues as far as our lectures are concerned? Please unmute yourself and make a comment. Or any other person, can you unmute yourself? Let me see. Now, in your class, unfortunately, because of all being online, it will be one of those first classes I won't be able to know I won't be able to put people's faces to the names. Okay, let's see. Kato Ali, just make a comment quickly, one second. Make a comment as far as our lectures are concerned. Are there any issues? Claire has already told us that the recordings are not being played because of license issues, but I think that has been sorted out. And if you continue experiencing the same problem, let me know so that we can resend them. Because yes, I understand there were some license issues. Kato Ali, please unmute yourself and make a comment quickly before we dive in. Okay, let me see if there's any other issue. Okay, so Kato Ali says that there are no issues. Okay, good. Good, and I hope it continues like that. As you know, we have issues of security. I hope none of you was affected yesterday in any way, either by having your relatives or your friends or classmates who were caught up in the unfortunate things that had happened. Like I always tell your group of people, I think what is important is to remain resilient, be on the lookout. Do not let these sad moments really, how best do I put it? Do not over-concentrate on what is happening. Concentrate on have a positive attitude and look out for the best. I know that we have gone through 2 years of hell with Corona and now with the bombs. But as you remain vigilant, both looking out to make sure that you do not get Corona, but also making sure that you do not become a victim of what is happening. Yes, so just be vigilant and be on the lookout. Don't be complacent and try to remain positive so that, life has to continue. And since life has to continue, it means we have to look out for the best. Okay, I think now we are ready to start our lecture. So today we start a new topic, which is basically data compression. Okay. Yeah, let's so again, if I may try to remind you about the communication diagram. Communication diagram, that is a very important diagram I keep sharing now and again. Okay, so if you remember our communication diagram, okay, we say that the first block is source, the source encoder. Okay, we say that the second block is a channel encoder. Then we say that this block is our digital modulator. And of course, we know this is our famous channel. Then we have a digital demodulator. Okay. Then we have a channel decoder. Then we have a source decoder. Okay. Of course, this is our information which we are trying to send. We say that under the source decoder, remember, this is a digital communication system. The whole of this is our transmitter. So this remains our transmitter. Let me just use an abbreviation like I normally like to. This is our transmitter. So this is our transmitter. Okay. This is our receiver. This is our receiver. And of course, this remains our channel. So if you look at it, it still pretty much looks like what we had at the very beginning, where we say the communication system is basically comprised of the transmitter, of the channel, and of a receiver. But in a digital communication system, we enter inside the transmitter and the receiver and break them down into separate phases. If you remember, this is the signal. Basically, this is our source, and this source comprises of a signal. Okay. And of course, even here, you're going to have, let me call it S. So our source, oops, what have I done? Our source S comprises of the signal, okay? And of course, this is our source. We use S with a squiggle because now this is the information that has been decoded, has been received and decoded or demodulated. Then we say that inside the source encoder, if we have an analog signal, remember we say that most of our signals are analog, and we spent a great deal looking at the different types of signals. Even in this particular course, I went through again to try to remind you the different types of signals. And we say that most of our analog signals are analog in nature, okay? And so as a result, because they are analog, we need to transform them to a digital form. Why do we have to transform them into a digital form? Because we are going to transmit them over a digital communication system. Okay, so we looked at signals, signals. Then we looked at the data analog to digital conversion. And we say that this analog to digital conversion is what we call source coding. But this type of source coding is what we call lossy source coding. And all that is doing basically is performing this function of analog to digital conversion. We therefore say that if our information is already digital in nature, then we have what we call data compression. Data compression, it too is source coding. So in source coding, you have two functions. You have the analog to digital conversion and data compression. You have the two functions, the analog to digital conversion and data compression. Now, this data compression is what we call lossless source coding. Now, you remember when we are looking at analog to digital conversion, we say that the process of especially quantization leads to an error, and we called that error quantization error. We went through the whole process of trying to find out how you find the signal to quantization error. And if you find the signal to quantization error, all you're trying to find out is how much error has been introduced as a result of quantization or as a result of the different processes. Of course, we say that in analog to digital conversion, there are three processes. There is the sampling, there is the quantization, and then finally the encoding. Okay, so that is why we call it source coding. It is basically forming and transforming an analog signal to a digital signal. So now today we are going to look at data compression. So this is what we call lossless source coding. And mind you, whatever we do at the transmitter, we also do at the receiver. Now you notice that most of the time I pay attention to the transmitter. I don't normally go and pay attention to the receiver. But I want you to always bear in mind that whatever happens at the transmitter must also have an impact on the receiver. Okay, so today we are going to look at data compression, which is another form, as I've already told you, another form of source coding. Okay, now this data compression, let me just a minute. This data compression can be in your books especially the common book which you have, Simon Heckins. It can be found in chapter 9. This data compression, and I'll use them. Concurrently. Sometimes you will hear me talking of source coding. Other times you will hear me talking of data compression. But I'm really talking about the same thing. Okay, so it is chapter 9 in your Simon Heckins. If you look at chapter 9, you will see some of the things that we'll be talking about. And then, of course, there's this digital to digital communication by John Prowakis. Yeah, it's also there. You can look for it. And then also there's this other book, Introduction to Digital Communication by Ali Grami. It's also in that book. Where does data compression find application? Now, I always like to start using this because, like I told you at the very beginning of our course, digital communication can really appear abstract. And some of the things that we do talk about really do not make any sense. It is difficult to appreciate how they find application. So when I'm teaching this topic specifically, I like to start with the application. Because as you will discover shortly, there's a lot of abstract in this, especially in this topic. Some of the things that we do talk about don't make any sense. So data compression finds application in that, of course, in storage systems, okay? Digital storages, that's where we actually find application. That's very common. What are some of the storage systems in digital communication, sorry, in digital in digital? It's basically you have things like CDs, DVDs, and all that kind of stuff, okay? So that's where we normally find application. Of course, the first application was in the Morse code. These days, we really don't use the Morse code. That was the most, I think that was the first form of communication in terms of digital, where we were using Morse codes. You can go and read around them. It's really more of history than anything. I'm not sure if there's any application. I'm not sure if anyone still uses Morse codes because the technology has advanced. We really don't need to use Morse codes. Yes, but currently we use a lot of data compression in MPEG and JPEG. Can someone tell us what MPEG stands for? You are always having, when you take pictures, you save them as JPEG. When you're having downloading your music, you save them as MPEG. Of course, I know these days we have things like Spotify, we have Netflix and all that kind of thing. So we not necessarily need to download videos. We have YouTubes and all those kinds of things. Basically, we have online resources which are continually streaming information. And these days we actually save our information even on the cloud. So as a result, we are no longer over downloading pictures and videos and all that kind of thing. But I'm sure when you take a picture on your phone, you normally save it as a JPEG. When you take a video on your phone, sometimes you save it as MPEG. Can someone tell us what MPEG or JPEG stand for? Quickly. Can someone tell us what MPEG is? Moving Picture Expert Group. Okay, that's good. And then also JPEG stands for Joint Photographic Expert Group. I know when we are doing communication, especially when you're doing telecommunications, there's a lot of abbreviations, as you will discover, and sometimes you can be lost behind the actual words. We're always talking of 4G, 3G, MBs, broader, all those kinds of things. So there's a lot of that. So we use data compression in those two things. I think you are familiar with that. The common one which we use, of course, like I said, these days we do save our information on the cloud, so we are not really that worried about how to transmit files or how to email. Remember, you email your files and then they are too big, and then they are telling you, oh, now you know what, your files are too big, they cannot really be emailed, or they are too large. So we use what we call the zip files, okay, or zip formats, and I'm sure you have used this quite a lot, okay? Like for instance, on our email, the Makerere email, there's a limit as to how much you can actually email a file over our network. And so in most cases that you have to use zip files or use zip formats to actually to transmit your information. And what you're really doing, you're using data compression. Can someone give us an example of the zip files that we commonly use on our computers, or file? Some of the formats that we do use. Can someone tell us some of the formats that we normally use? Let's see, someone has already told us. That's very good. Okay, we have WinRR, which one? That's actually a very common, and I think we have used this one for quite some time. Then we have the WinZip. Yes, that's very good. So every time you're doing that, basically what you're doing is that you're compressing your file, okay? You're compressing your file. You're reducing the amount of, So every time you're doing that, I want you to remember that you're compressing your file, okay? That's very good. So WinZip, I think, is one of the very old ones, and this WinRR is also one of the old ones. And there are many other formats, okay? So that's one of the applications where data compression finds application. The other one is encryption. We use a lot we use data compression under encryption. Can someone give us an example of an encryption? What do we mean by encryption? What is data encryption? What are we trying to do? Can someone tell us what data encryption is all about? What is data encryption? What are we trying to do when we encrypt a text or encrypt information? What are we really trying to do? Okay. What are we trying to do? Yes, trying to secure your data. That's very important. Especially in this day and age, there's a lot of encryption, a lot of security issues. You don't want people to eavesdrop your information, and neither do you want people to hack into your information. You want to secure it. So we use a lot of encryption. So data compression also is used in encryption. Of course, the old ones, which you know very well, is the CDs and DVDs. We do use a lot the CDs and DVDs kind of, I told you about the storage, okay? CDs and DVDs use a lot of data compression. We also use data compression in speech and speech patterns recognition, okay? This is also, that's where it finds a lot of application. Actually, at the very beginning, when they were developing data compression, of course, now we've gone through different phases, and there are different usages which they have found as a result. But at the very beginning, it was used for speech recognition and patterns. Okay, so but now it has found quite a lot of application. Okay, it has found quite a lot of applications. Of course, we as much as I'm saying this, but you will find that when you're dealing with digital communications, especially when you're dealing with things to do with what we call it, signal processing, you actually use a lot of data encryption. Okay, yeah, so we are not really going to go through this. Of course, what we are covering in this topic are really the basics of everything. So in future, when you finally find yourself working on this, either in industry or academic, you're doing an academic qualification, like maybe your master's, then you look at this more plainly. Okay, so that's why I always want us to start with this, because I don't want you to get the impression that it's very theoretical. Now, the next parts which we are going to look at really are very abstract. So that's why it is important for us that we start looking at the actual application. So I've already told you that data compression is basically lossless source coding. What are we really trying to do? You remember, in any communication system, we always have only two resources. It is a bandwidth or power. As a communication engineer, our role is to make sure that we efficiently use our bandwidth and power. Of course, I know that over the years we have expanded, and now we can use different bandwidth and different wavelengths. Okay. However, those bandwidths and wavelengths that appear, they are not going to stretch. So it is up to us to make sure that whatever we want to do is done in those bandwidths. And there's nothing else we can do. We just have to make sure that we use that properly. So therefore, what is the role of source coding? Or like I said, bear with me. When I talk of source coding, I will use them interchangeably. I will either talk of source coding or data compression. And I'm using them concurrently. I mean the same thing. But you must remember that even under source coding, we have two functions there. There is the lossless source coding and the lossy source coding. The lossy source coding is what we call the analog to digital conversion. So in this particular case, I'm referring to data compression. Please make the distinction and don't get confused, because you need to find out what's the difference. So anyway, as we try to make sure that we use our resources properly, so the role of data compression basically is to efficiently represent the information or the data, in this case, that we have generated by the source. Sorry, of course, who is generating this data is our discrete source. But we want to make sure that we represent it properly. Okay, and we want to make sure that all the information that we want to transmit fits into the given resource, in this case, the bandwidth that we have. So how do we do that? We do this by using the source encoder. Okay, we use the source encoder. We compress, the whole process of compressing the information is done by a source encoder. In most cases, right now, it is not really a requirement, but originally, most of the source encoders that we did have required statistics. What do we mean by this? It means that we needed probability, because you can remember, when we're talking of random signals, you are talking of random signals which are not predictable. They are characterized by statistics. So therefore, you need to analyze them using probability or statistical averages. So in most cases, your source encoder would be required to actually have statistics. Now, technology has really changed. Most of the source encoders that are on the market right now do not necessarily have to have statistics. And in any case, the information you're transmitting is quite large. There's no way you can really keep up with the statistics. Okay, so you're using lossless encoding, and you want to efficiently represent the information that you're generating by the source. And of course, you do this using the source encoder, and this source encoder requires statistics. Now, this process, like I've already said, is known as compaction or compression. Okay, and as the name suggests, what does it do? It involves removing redundancy in the information to be transmitted. Now, the information that we do transmit contains a lot of redundancy, especially when it comes to speech. The good example I always like to use is the Luganda. And for some of you who are Baganda, you will realize that there are some words which are very common. Okay, like I don't know which particular one to use. I always like to use the word. Let me see something like. Okay, let's speak up. The one I like to use is a bit gross, but let me use this particular one, which is come to mind. For instance, you have things like amate, then you have namata, then you have, there are some words which continue being the same, sounding the same. In Luganda, for instance, you have a lot of words which are double letters. For instance, things like namudu, okay, or dungu, or something like that. So it's like you have repetition, which is not necessary. So sometimes some of that repetition, you need to remove it. And when you're removing this repetition, you have to make sure that the information does not lose its original meaning. In other words, the fidelity of the information is not compromised. The same applies to English. In English, we have some words which are pronounced the same and not necessarily the same spelling. Okay, they are pronounced the same, but not necessarily the same spelling. For instance, you have things like desert or dessert, okay? Or you have things like meeting, as in meeting, or you have things like to meet, or meat, as in the food, okay? So those are some of the things which you can actually think about. So when it comes to data compression, what does it do? It removes redundancy, especially in speech. Of course, right now it has evolved, like I told you from the very beginning, it has evolved beyond speech. Okay, it has gone into several other things. So, so there's really, it has found application in many more things, but initially it was concentrating on speech and the English alphabet. Of course, for obvious reasons, that the people who drive the technology are normally English speakers. Okay, so data compression is basically as a result of, is basically under the, it's the one, when we're looking at data compression, we are basically looking at the information theory, okay? Because we have source coding and we're trying to make sure that the information which we are coding is going to be transmitted over a channel, okay? So now the question is, how do we make sure, or how do we measure the quantity of information? Okay, first we have to make sure how much information do we have, and then how much are we going to be transmitting, and how much is going to be received on the other side. And even when we have received it, has it been received in error, or it is the actual information that we are trying to, or was transmitted. Okay, so this was basically addressed, is addressed under communication theory. Okay, of course we say information theory. Now, like I still told you at the beginning, digital communication is basically a continuation of communication theory. Okay, so a lot of this work was done. Of course, we are dealing with probabilities, so there's a lot of mathematical modeling and analysis of communication systems, but a lot of work was actually discovered or laid down by Shannon. Okay, now Shannon is the father of basically of information theory. Now, in our part, the information theory that we are really going to look at, or we have already looked at, is basically, in this case, we are going to be looking at source coding. And then after source coding, we shall look at channel coding. Already we have an idea of information capacity, or information theorems, which we basically call channel capacity. Okay. And I hope you still remember how we define channel capacity, because I'm not with you, so I can't really ask you what channel capacity is, but I hope you still remember some of the things. Isiko, please do not disorganize our, Isiko, do not disorganize our communication, do not disorganize our work. Okay. So the theorems basically that we are going to be looking at, or what Shannon did in this, for this particular case, what did he really look at? So since we are looking at source coding, we are looking at the efficient encoding of our source signal. Okay, we are looking at the efficient coding of our source signal. So if we have encoded our signal, what is the next thing that needs to be done? It has to be reliably transmitted over the noisy channel. It has to be reliably transmitted over the noisy channel. And the next question is, how much of that information can actually be accommodated or transmitted over the channel? And this we saw under channel capacity. And maybe let's ask ourselves, can someone tell us what channel capacity is? What is channel capacity? What is channel capacity? Can someone post the answer in the chat room? So what does it tell you? Tell you that channel capacity has not left you. It is also going to be one of those questions that you'll be receiving now and again. What is channel capacity? Can someone tell us what channel capacity is? Just to remind ourselves. What did we say channel capacity is? What is channel capacity? I'm waiting for an answer. I'm waiting for the answer in the chat room, what channel capacity is. Okay, someone has answered. So the maximum rate at which data can be transmitted in a channel. That's very correct. The rate of which data is transmitted over a channel in bits per second. That's also correct. How do we increase the channel capacity? Okay, I can see Godfrey saying is defined as the maximum rate at which information can be transmitted through the channel. That's correct. So how do we increase the channel capacity? Do you remember? How do we increase the channel capacity? How do we increase the channel capacity? We increase the channel capacity by increasing the signal to noise ratio. That's very correct. How else do we increase the channel capacity? Do you remember? Apart from signal to noise ratio, we increase the channel capacity by increasing the bandwidth. Okay, that's very good. I can see people are still remembering. Okay, and someone else has also posted. Kato Alice is saying increase the power, we increase the bandwidth to a certain limit. Kevin, that's very good. Of course, we can increase the bandwidth, but we cannot increase it indefinitely. Yeah, that's very good. At least people are still remembering. That's good. Okay, so Shannon information theorem is basically, in our case, is based on the efficient encoding of the source signal. It also takes care of the reliable transmission of the message signal over the noisy channel, and also takes care of the information capacity theorem, what we call channel capacity theorem. So in this case, we have three theorems. In other words, Shannon addressed three theorems. For this particular data compression, we shall be looking at the Shannon source encoding theorem. When we go to channel encoding, we shall look at Shannon channel coding theorem. And we have already looked at the theorem of channel capacity. Okay. So source coding is motivated by two factors. And of course, we have already said what drives this. We say that most times in most of our speeches, the raw information is basically having a lot of redundancy. So what are we trying to do? We try to make sure that we remove the redundancy. And when we remove the redundancy, it means that we are making sure that we do not waste our primary communication resources. And in this case, we are not going to be wasting power. In other words, data compression improves the bandwidth efficiency. Okay, you remember? Draw a block diagram of a communication system and briefly describe the function of each block. Data compression improves the bandwidth efficiency. How does it improve the bandwidth efficiency? It makes sure that you remove, if you make sure that you remove redundancy, it means that there's a lot of information that you can actually pack on this particular channel. So that's the main role of data compression. Of course, as we have already seen, there are many other advantages that we have discovered as a result of using data compression. For instance, we can transmit, we can store, we can do all sorts of things. Now we can even do encryption, but the main reason was to make sure that the information that we are transmitting is compacted. In other words, we are feeding a lot of information in one small resource. Okay. So the transmission of which is, when we remove redundancy, it means that we are making sure that we are having a lot of information that is going to be transmitted. Okay. So for efficient signal transmission, of course, we remove the redundancy that is really basically repetition. So let's go to this Shannon's fundamental source coding theorem. What does it say? Okay, it's also known as Shannon's source coding theorem. It says that given a discrete memory source characterized by a certain amount of entropy, the average code word length for a distortionless source encoding scheme is upper bound by Is entropy. I know all this sounds abstract, but don't worry, very soon all this is going to be clear. The only thing I want to remind you here is that you remember what we said about memoryless? We say that whenever we see the word memoryless, because now we are talking of a memoryless source encoder. Remember, the other time we are talking of a memoryless channel. Then we talk of memoryless symbols, memoryless codes, memoryless sequences. Every time you see this word memoryless, it means that the information, for instance, in this case, this is the encoder. So it means that the encoder is giving independent signals or independent source signals. What does this mean? It means that the signals are not correlated. Okay, that's what I want you to pick from here. They are not correlated, they are independent. The probabilities are not dependent on each other. The time slot T is not dependent on T minus, or neither is it dependent on the future, which is T plus. Okay, that's what we mean. Entropy is the average of information. We shall just see shortly what that means. And then, of course, so for now, let's just continue. So, but that is basically Shannon's source coding theorem. Okay, if you remember your probability, okay, if you remember from probability, and okay, the best way to demonstrate this is basically to, okay, just keep this slide in mind. Let's just go through it and then I will demonstrate shortly. So for a discrete moment source with an output S modeled as a random variable signal from a finite alphabet, and of course we have that probability, we know that the summation of the probability of any of the information, in other words, in this case, since we are talking about probability and talking of information, we are talking of the source. So the probability of the source should be equal to 1. The total probability should be equal to 1. So, and if we have any source that is pk, which is equal to 1, it means that the rest of the other information is there, the probability of the other information is equal to 0. And remember this source, if the symbols are emitted with a low probability, then we may know that there's a surprise and there's a lot of information. But let me just demonstrate before we continue so that we can be together. So what do we mean by that? Let's imagine that we have QPSK. How many symbols are in? How many bits per symbol does QPSK have? How many bits per symbol does QPSK have? I'm expecting an answer in the chat room. How many bits per symbol does QPSK? So N is the number of bits per symbol. Okay, so we can see, okay, thank you very much. So we know that N is equal to 2. So if N equals to 2, how many symbols does QPSK have? If N equals to 2, how many possible symbols does QPSK have? Thank you, Kevin. Thank you. So, okay, I see an answer as well. So if N equals to 2, it means that we have 4 possible symbols. So our sample space of QPSK, the sample space of QPSK is basically equal to what? We either have 0, 0, 0, 1, 1, 0, or 1, 1. Okay? So that is our sample space. So we can as well say we have S0, S1, S2, and S3. Okay? S1, S2, and so forth. So this is the sample space. In other words, this is the possible symbols that we can generate if we are using QPSK. If our source is QPSK, this is the possible symbols that we can generate using QPSK. Okay. So what about the probability? What is the probability of transmitting S naught. What is the probability of transmitting S naught? What is the probability? Remember, we are saying there are 4 possible symbols. So our the sample space is 4. Okay. So the probability, thank you very much, Ronald. The probability of transmitting S naught is equal to 1/4. Okay. What about the probability of transmitting S1? What is the probability of transmitting S1? What is the probability of transmitting? So the probability of transmitting S1 is 1/4. The probability of transmitting S2 is, what about the probability of transmitting S2? So the probability, we know very well that the probability of, so let me just do this, remove this one. So in this case, the probabilities are equal. So the probability of transmitting, what's going on? Of PS1, S0 equals PS1, which is equal to PS2, which is equal to PS3, which is equal to 1/4. Okay, so that is the probability. So the summation of this QPSK for K from 0, let's start with small k, to 3 of P K should equal to 1. And we know we can prove that because we know that the probability of P1 plus the probability of P2, sorry, S1, S2 plus the probability of S3 plus the probability, there's one I've missed out, S0 is equal to 1, which is basically 1/4 plus 1/4 plus 1/4 plus 1/4, which is equal to 1. Are we together? Now, let's assume that the probability of these symbols were not the same. Let's assume that the probability of S0 is not equal to the probability of S1 is not equal to the probability of S2 is not equal to the probability of S3. Still, this equation stands. Still, that equation stands. However, if the probability, okay, let me find out. If the probability of S1 is equal to 1, what is the probability of S0, the probability of S2, and the probability of S3? If the probability of S1 is equal to 1, what is the probability of S0, S2, and S3? That's correct. This means that the probability of S0 is equal to 0, is equal to 0, is equal to 0. That's very correct. That's very correct. And I'm glad that you are understanding this very well. That's very good. So this is what I was trying to communicate. Now let's take this a step further. Let's take this a step further. We get the probability of this by loop. So we get what we can call the information from the probability. That's why we're saying that the source encoder must know the probability of the different symbols that it is actually generating or encoding for this case. Okay. Now we call information I of S0. Let me use SK. The probability of the value of information I of SK is given by the log of 2 PK. Information I stands for information is equal to the log of 2 PK. So what does this mean? What happens if PK, oops. What happens with PK What's going on? If pk is equal to 1, what is the value of information of sk if pk is equal to 1? What is the value of information if pk is equal to 1? Or if pk is equal to 0, or pk equals to 0. Okay. So yeah, so if pk equals to 1, if pk equals to 1, it means that this is equal to 0. And if pk, oops, if pk equals to 0, if pk equals to 0, oops, I don't know how best to control. Let me just how best. So the value of information of sk, if pk equals to 0, how much is it? It's very, very large. Okay, someone is saying 0, 0. That is not true, but it's very, very large. So what do we draw from this? What we see from here is that if the probability of generating a symbol is very small, if the probability of generating a symbol is very small, let me use mathematical signs. If the probability of generating a symbol, if pk is very, very small, if pk is very, very small, I don't know how we use small. Okay, very, very small. How do we normally use very small? It means that we have a lot of information. If pk is very, very small, it means that we have a lot of information. If pk is very, very small, it means that we have a lot of information. Okay, so the less the probability, the more the information. Let's go back to our slides. So basically, that's what I've just been trying to demonstrate. Okay, if pk equals to 0, it means that the rest of the other symbols are. So if pk equals to 1, it means that the rest of the other symbols are equal to 0 for all I which is not equal to k. And if pk is equal to 1, it means that we have emitted. If the symbols are emitted with very low probability, it means that there's a lot of surprise. In other words, we're not expecting these probabilities. We're not expecting these symbols to be transmitted. And because we're not expecting them to be transmitted, we have a lot of information. For instance, I always like to use the example of being born in Uganda or being born in the equator, on the equator or at the equator. What is the probability that the sun is going to rise tomorrow? What is the probability that we're going to see the sun tomorrow? You post your answers in the chat. What is the probability? This is the example I really like to give. What is the probability that the sun is going to rise tomorrow? So the probability that the sun is going to rise tomorrow is 1. Why is it 1? Because we are at the equator. We have never been, there's never been a day when there's no sun. Okay? For instance, even if we have the so-called equator, sorry, the eclipse and whatever, there will be no day where we do not see sunshine. Unlike those people who are at the North Pole, there are some days when they don't see the sun at all. But for us, because we're at the equator, we see the sun. So we are not surprised. In fact, we would be surprised. Let me ask it the other way around. What is the probability that what is the probability that tomorrow will be in full darkness? What is the probability that tomorrow will be in full darkness? What is the probability that tomorrow will be in full darkness? Yes, so I've asked the same question, but the opposite. We will actually be very surprised if we woke up tomorrow and there's no sun and we are in total darkness. That's why we get excited when we are seeing the eclipse, because we are not used to seeing that. And remember, the eclipse don't happen. So the surprise is where we get the information. So when something is very obvious, when the probability of the source is 1, there is actually no information. When there's no surprise, there's no information. Okay, that's why even in communication, we are not interested in deterministic signals, because the deterministic signals do not carry any information. Probability is where we find our information. When we have a low probability, that's where we find information. So that's why this statement is trying to explain basically what this statement is saying is that when the probability is very low, when the probability of the source is very low, we get surprised and there's a lot of information. But if we know that all we are going to be generating is a 1, 1, 1, 1, 1, then we are not surprised, and neither do we find information. Okay, so this is what I've already told you, that we measure information in terms of this expression. Okay, and I want you to take note, because normally most of the students make a mistake. Oops, sorry. Most students make a mistake. They always forget this is to the base of 2. Okay, this is to the base of 2. Do not forget that. Okay, so information is basically the log, actually, I think sorry, I gave you the wrong expression at the very beginning. I gave you the wrong expression at the beginning. I retract that. I gave you a wrong expression. The probability of information is basically given by the log of 1 over pk. 1 over pk. I'm very sorry. I gave you a very wrong information. I'm very sorry about that. So that's how we measure. And of course, we have also gone through this already. So if we have the log of the information of is equal to 0 if the probability equals to 1. The information is there if the probability is between 0 and 1. Okay. And then we have the information of sk is greater than si if the probability of sk is less than the probability of si. And the probability of sk, sorry, the information of sk and sl is basically given by the information of sk plus si. Why? Because they are statistically independent. Remember, we said that they are not correlated. That's what we said. So that is basically how we find information. Okay, and this is the properties of information. These are straightforward probability. Okay, so that is information. So next, what is entropy? Remember from our description, okay, of source coding theorem, we say the given a discrete memory source characterized by a certain amount of entropy, the average code word length of a distortionless source encoding scheme is upper bound by entropy. I see someone is asking a question. Let me find out. What's the essence of finding information? Tumsime Ian, you did not come early. If you had come early, this question was answered at the beginning. So you are a late comer, Tumsime. Find out from your friends. That's exactly, for those of you who started with me, that's what I told you, that I always try to start by finding the applications, because this is very abstract. It looks like a history lesson. And that's why Tumsime, who joined us very late, finds this information irrelevant. Tumsime, next time, please join the class early. Then you will not be asking me this question. So I'm not going to answer that. Ask your friends what I told them. Okay, so where are we again? So next, so we have found what information is. Next, we need to find what entropy is. We found what, okay, someone is complaining, my internet is stable. Unstable internet. Can someone hear me? Are you hearing me properly? Can you please type yes if you're hearing me? Ivan Kaketo, can you type yes if you're hearing me, because you are the one who is complaining? Okay, so maybe Ivan, you are the one who has a problem. Okay, now you can hear me. Okay, maybe the problem is on your internet. Okay, so we have seen what information is. Next, we need to find out what entropy is. What is entropy? We define entropy normally by H. So the entropy of a sample space, which is basically S, is given by that expression. The entropy of the sample space is given by that expression. Okay, and as you can see, the entropy of S is the summation of pk times information. The entropy of S, the sample space S is, and when I say the sample space, I mean the possible number of symbols in a given, a given source. like we took an example of QPSK and we saw that it had 4 sources, 4 symbols, 4 possible symbols. So in this case, the sample space of QPSK is 4. And so therefore, if the sample space of QPSK is 4, it means that you have the probability of all the symbols which you sum times the information, then it gives you what entropy is. What is really entropy? Entropy is a measure of the average content per symbol. Entropy is the average measure of content per symbol. We look at entropy as the number of bits per symbol. You can actually look at it as the number of bits per symbol. Okay, you can look at it as the number of bits per symbol. Okay, and again, the how do I put it? The properties of entropy, remember, just like you had the different properties of information, the properties of entropy are also derived from that particular expression. Okay, as I was trying to explain earlier on, the entropy of the source is upper bound. It's the same thing. The entropy of the source is upper bound by the number of bits per symbol. Okay, it's the upper bound by the number of bits per symbol. What does K stand for? K stands for the possible number of symbols. K stands for the possible number of symbols. Okay, here we are using the word radix, but you know radix is basically the number of possible, like if you're dealing with the radix of 10, you're saying that you're counting from 1 up to 10. So those are just basically the number of symbols, the possible number of symbols for any given source. Okay, so if you have QPSK, you have 4 possible number of symbols. So the log of 2 of, maybe let me demonstrate so that we are together on the same page. So if we use the example of QPSK, which we had, we said QPSK has 4 possible symbols. QPSK has 4 possible symbols. So we say the sample space of QPSK has 4 possible symbols, which we said is basically 0, 0, 0, 1, 1, 0, 1, 1. And this is S0, S1, S2, and S3. We say that the probability of S0 is equal to the probability of S1, which is equal to the probability of S2, which is equal to the probability of S3, and is equal to a quarter. Okay, so K here is equal to 4. Okay, so we are saying that the entropy is being upper bound by what? It's upper bound by the log of 2 to the power, sorry, of the log of 2 of 4, which is basically equal to 2. Okay, if K is equal to, let's say 7, because you can actually have that in digital systems. Okay, you can have 7. It would mean that the entropy of that source H, let me call it S squiggle, is basically the log of 2 of 7, which is equal to, you can find out what that equals to, maybe it's 2 point something. Okay, so that's the entropy. Entropy is basically the average content per symbol. And in this case, since we are dealing with bits, it's basically the average number of bits per symbol. Okay, remember what we said? We say that if these symbols are not the same, in other words, if the probability of these symbols is not, they're not equal. Okay, if the probability of these symbols are not equal, okay, and we said that supposing let's say P S1, so S1 was equal to 1. We say that P S0 is equal to 0. It's equal to P S1, sorry, S2, P S3, which is equal to 0. Okay. Therefore, the entropy of the sample space, okay, would be equal to 0 if Pk if n of the symbols is equal to 1. In this case, if n of the symbols, and in this case we have PS1 equals to 1. And this is mainly because remember what we said, that the information, there's no information if the probability is equal to 1. And there's a lot of information if the probability is very, very small. Okay. And then of course, we know that if the probability, again, from the other expression which we had, okay, the entropy of the sample space, this which we have just said, is basically like, for instance, for QPSK, the entropy of QPSK is basically equal to what? The log of 2 of k, in this case, which is 4. Why is it this case? Because we saw that the probabilities are the same. The probabilities of QPSK are the same. So the probability of equal probable symbols, so if the probabilities are the same, and in this case was equal to 1/4, it means that the entropy of QPSK is basically the log of 2 of k, which is 4, and it is equal to 2. Okay, so the entropy is basically the average content per symbol. Okay, so maybe we can go back to the slides. Okay, we can go back to the slides. Okay, so basically that's what this slide is trying to explain. That's what this slide is trying to explain. Okay, so the probability, the entropy of equal probable symbols is given by that expression. Of course, we know what that is. Okay, so the entropy of a binary memory source then is therefore can be drawn like that. Okay, as we can see, the entropy approaches 1 when the probability is equal to 0.5 and then falls back to that case. Okay, so that is the entropy of the source. Now, what happens when you have, maybe what happens when you have symbols? For instance, you remember in probabilities or in a communication system, you can have a scenario where you have 2 possible symbols. What is the probability of this given that you transmitted that? What is the probability of that given? It means that you have a sample space which is basically extended. And an example we can look at is what would be the probability of, for instance, of drawing a die. And maybe let me ask, what is the probability of scoring a 1 on a fair die? Excuse me. What is the probability of having a 1 on a fair die? Can someone post the answer in the chat room? What is the probability of having? It's 1/6. Okay, it's 1/6. That's correct. What is the sample space? Can someone write for us the sample space of a fair die? Can someone write for us a sample space of a fair die? The sample space of a fair die is 6. Akol, that's correct. Can someone write for us in the chat room the actual sample space of the fair die? Can someone write for us the actual? Yes, it is 6. That's correct. But can you write for us the sample space? In other words, can you write for us the possible symbols? Yes, that's correct. It is 1, 2, 3, 4, 5 up to 6. You are very right. So that is the sample space. Okay. So if that is the sample space, can you work out in your notes? Can you work out the entropy of the fair die? Can you work out the entropy of the fair die? First and foremost, what is the information of getting a 6 or generate? What is the information of generating a 6? Can you post for us the answer for the information of generating a 6? What is the information of generating a 6? In other words, what is contained in generating a 6? Can someone post that in the chat room? What is the information contained in generating a 6 of a fair die? What is the information contained in generating a 6 for a fair die? Quickly, can someone post that in the answer? Sorry, can someone post that in the chat room? What is the probability of scoring or generating a die, generating a 6E in a fair die? What is the probability of generating? What is the probability? So the sample space. So the sample space is S1, S2, S3, S4, S5, and S6. Okay, that's our sample space. Okay, what is the information of S6? What is the information of S6? Can someone post that in the chat room? Remember what we said? We said information of SK is basically equal to what? The log of 2 of 1 over PK. So therefore, we are saying that the information of S6 is equal to the log of 2 of 1 over 6, which is equal to, according to Ronald to Maramie, is saying is 2.584. Okay. So if that is the case, so what is the entropy of S? What is the entropy of S? What is the entropy of S? Where S is our sample space of a fair die. What is the entropy of S? The entropy of S is basically the summation. You remember what we said? The summation of I of PK IK from K is equal to 1 up to 6. Okay, which is equal to, I'm waiting for your answer in the chat room. Please post your answers in the chat room. I'm waiting for it. What is the answer? So in this case, it is what? PK is 1 over 6. So it's 1 over 6. 1 over 6 times 2. What was the answer again? 2584. Times 6. Why is it times 6? Because we have 6 possible samples. We have 6 possible samples. And these samples are equiprobable. In other words, their probability is the same. So it's the same as saying plus 1 over 6, 2584, plus 1 over 6, 2854, plus up to 6 times. That's what it means. So the entropy of this sample space is basically HS, the log of what? Of 2, 6. Okay, that's what we said. Why is it that? Because it is equiprobable. If it is not equiprobable, then we follow that formula. If it's not equiprobable, then we follow that formula. But even this formula still stands. The only difference is that this 6 is going to cancel out. That 6 is going to cancel out because we are multiplying this by 6. So this 6 is going to cancel out with that 6. Okay. Now, in a communication system, we normally have what we call joint probabilities. In a communication system, we normally have what we call joint probabilities. Okay. And when we talk of joint probabilities, normally it's like you have SSS. So if we are dealing, for instance, in this case with a fair die, if we are dealing with a fair die, it means we have S1, S2 up to S6, okay? And if we throw this die twice, S6, the joint probabilities of this fair die are basically going to be, what is the joint probability of throwing, in other words, what is the probability of throwing the die twice? Or the other way around, what is the sample space of throwing a fair die twice? What is the sample space of throwing the fair die twice? What is the sample space of throwing the fair die twice? It is 36, okay, that's correct. Because you have S1, 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 S2, S1, S6. And then you have S1, S2, S1. It's the other way around. It cannot be the same. This is S1, S1. So this will be S1, S2, S6, S2. Okay. And then when you go like this is going to be S2, S2. And then you have S6, S2. And then here you will have S2, S6. And then here you have S6, S6. Okay. And Kevin has made life very easy for us, and he says that the probability of throwing a fair die, in other words, of SI, is equal to 1 over 36. And Kevin, you're very correct. That is 1. So if that is the case, what is the information? What is information contained in? What is the information contained in that one? If that is the case, what is the information? Can you give us the information? Remember, information is equal to information of SK, SI is equal to, remember, the log of 2 into 1 over P, PK. In this case, okay. Do you still remember the probability of S1? What was the probability? You remember? It was how much? It was 2.5. What was the probability again? Does someone still remember what the probability it was? What was the probability?
2.584.
Yeah, the probability, sorry, the information was 2.584. That was the probability. And we are saying that the probability of these ones is equal to, someone has calculated for us, but we shall, what was it was 5, the probability is 5, not the probability. The information, you forgive me, I'm just confusing you. The information is 5.17. Do you see what is happening? Something has happened, okay? The probability, the information of this is twice the information of this. The information of this is twice the information. The information of this is twice the information of that. The information of this is twice the information of that. If we go back to the slide, if we go back to the slides, does the information have units? That's very nice. Does information have units? Yes, information does have units. What is the unit of information? That's a very good question, Godfrey. What's the information of units? Sorry, what's the units of information? In other words, what is the scale of information? What is the scale of information? Anyway, to just be fair, it is just bits. Of course, we are looking at bits. So we are dealing with information, so it's bits, okay? So information is basically bits, okay? That's what we are looking at. Entropy is bits per symbol. Entropy is bits per symbol, okay? Because remember, we are calling it the average rate of information. I don't know, is that the average rate? But yeah, it's basically the bits per symbol. Okay, it's bits per symbol. So what is the average information contained in the thing in the above? We have already calculated that. If the fair die is thrown twice, what is the entropy? I think you can calculate that. What would be the entropy? We can calculate that. I think we have already seen that it's going to be twice the amount of installed information. Okay, so we've seen that. So we can see that the entropy, first and foremost, we can see that the entropy is basically information, which is average information per symbol or bits per symbol, okay? The information contained in a given symbol. And then we have seen that this information is got from the probability. This information is got from probability. That's why I don't remember what was his name. Was it Ivan or I don't remember, Ian, who was asking us that where do we get this? He's already getting confused because it looks like witchcraft. No, it's not witchcraft. It's not witchcraft. For those who were the early worms, they realized that that was not witchcraft. It is real information. Okay, it's real information, and that's how we do it. So now you can see that the probability plays a very big role at the source. The source encoder, or the one which is generating the symbols that we are interested in. It is therefore important for us to know, in this particular case, what is the probability? What is the probability of generating a 1? What is the probability of generating a 0? What is the probability of 1? However, over time, and as technology has improved, we have actually run away from that. But for the beginning, that is what we are looking at, okay? Because we are studying the basics, and that's what we are basically looking at, okay? So the process of converting the source information into an array of sequences is what is basically important. And we do that, how do we do that? We do that either in what we call the binary sequencing. In that case, we are looking at 0s or 1. But we also have ternary, though we are not really going to go there. I don't think we'll go there, but I want you to note that when we are talking of coding, source coding, here we are mainly focusing on the binary bit of 0s and 1s. But you can go up to 3, you can go up to 4, you can go up to any number. And the current applications actually use more than binary, okay? How is this done? We do it through a source encoder, okay? So for efficient source coding, the source encoder must satisfy that the output of the source encoder is binary, like in the case of what we are looking at. And also it must be able to be uniquely decodable at the end. So in other words, when you reach at the receiver, you don't want to start confusing, was it a 0 or a 1? Was it a 0 or a 1? You want to be when it's very clear, okay? And then the average code length of a source encoder is given by that expression. The average code length of a source encoder is given by that expression, where LK is the number of bits per source symbol. That's why someone was asking me a few minutes ago, what is the units of information? The units of information is basically bits. Okay. Remember, what are we trying to calculate? We are trying to find the entropy. We are trying to find the average length. In other words, we're trying to find the number of bits that are going to represent our symbol, which we are transmitting. Let's imagine that we are transmitting a 6, and we are now trying to represent it using the binary. And we have seen how many bits we expect to represent this particular thing. Now, in practice, we don't use points in bits. We don't say that we're using 2.3, 2.0, no. Normally, we are using either 1 or 2 or 3, yeah, like that, okay? But we see that when we look at entropy, of course, when we are measuring capacity, we can go into bits in points, so that's okay. But normally we use wholes, not fractions. Okay. The next thing is that how do we measure the performance of our source encoder? We use what we call the coding efficiency. The coding efficiency is basically given by L mean over divided by the average code length. And as you can remember, the average mean, so in other words, the minimum code length is given basically by our entropy. The minimum code length is given by our entropy. Don't worry about this. We shall do an example to clarify how each of these ones are actually helping us. Okay. So if this is our average mean, okay, and this is our minimum, sorry, this is our average code length, and this is our minimum code length, it means that our average code length is greater than our minimum code length. And therefore, the coding efficiency is always less than 1, less or equal to 1. In other words, it's either less or equal to 100%. Okay, that's what it means. So when we go back to, now we are basically revisiting the source coding theorem. Okay, let's revisit the source coding theorem, because I know at the beginning it was looking very abstract. So if our L mean is determined by the source coding theorem, so how does the source coding theorem therefore read? It says that for a given discrete memory source of entropy, the average code length, okay, remember the average code length, for a distortionless source coding is upper bounded by its entropy. Okay, do you remember? Let's go back to the actual expression and see if we can make sense of it. Given a discrete memory source characterized by a certain amount of entropy, the average code word length of a distortionless source encoding scheme is upper bound by entropy. Now, when we go and feed in that expression, because now we kind of understand what that means. Okay, when we go now to the actual expression, okay, what does this expression mean? It means that if we are going to transmit any information, any data, any digital information, the codes which we are going to remember, because we say data compression takes out redundancy. So it means that we can come with, let's say we can come with 6 bits and represent them with 4. Or we can come with 8 bits and represent, or we can come with 4 letters and represent them with 2. Okay. It says that if we are going to have no errors, if we are not going to distort the information, then we must make sure that the new code which we are generating is going to be less than, sorry, it's going to be greater or greater than the entropy. Okay, it's going to be. So if we do not meet that condition, it means that we are going to introduce errors. If we do not meet that condition, it means that we are going to introduce errors. That's what basically it means. Okay, so the entropy represents the fundamental limit of the average number of bits per symbol. Okay, and therefore, again, if we go back to the coding efficiency, then we can represent our coding efficiency as the entropy over the average code length. Any questions so far? Any questions so far? But this will we get clearer as we actually do examples. So, but let me see if anyone has some questions. Are there any questions? Any questions so far? Okay, if there are no questions, then we'll just continue. So far we have, oh, there's a question. Okay, there are no questions so far, so we'll just continue. So far we have looked at some terminology, which you need to remember, and maybe you need to go back and revisit, make sure that you understand. We have looked at the discrete source, which we are trying to find. and we say that this discrete source must be memoryless. If it is memoryless, then we have the conditions we have. But if it is not memoryless, then we cannot proceed with the assumptions we are making. Remember, in engineering, we are always making assumptions. We are always making assumptions. We are making sure that the source that is generating these symbols, it is actually not correlated, because if it is correlated, then it means these conditions we have been talking about do not hold water. We have described what information is. We have seen what entropy is. We have also seen that the entropy is governed by Shannon's source coding theorem. We have also seen that each of those letters, so words or data, is going to be represented by a code length. And whenever we are measuring our source encoder or data compressor in this particular case, we have to see what is the efficiency. In other words, the efficiency shows us how much reduction. In other words, how if we have reduced the number of bits from 4 to 3, or we reduce the number of bits from 4 to 1. Remember, we are trying to remove redundancy from our words, from our information. So if we reduce our number of bits from 3 to 1 or 3 to 2, or we must make sure that in the process of reducing, we do not introduce errors. And that's what source coding theorem is trying to make sure. It is giving us a guideline so that when we do compressor information, we do not introduce errors. That's what Shannon's source coding theorem is all about. So once we have made sure that we do not introduce errors, the next question we need to ask ourselves is how much of the information how efficiently have we reduced? In other words, how have we used this bandwidth that we are trying to transmit more efficiently? If we reduce the number of bits from 3 to 4, is that good? Because remember, we are trying to remove redundancy. So if we reduce the number of bits from 3 to 4, are we really introducing anything? Are we introducing anything? It means that we are not doing it efficiently. Okay. It means that we need to reduce to make sure that we utilize our channel, we utilize our bandwidth as efficiently as possible. So the coding efficiency is very, very important. The coding efficiency is very, very important. Now, I'm not going through the different types of source encoders or source codes, but I'll ask you to go and look at them. Okay, there are different versions. Okay, we have the source encoding, which when it is achieved, either you can achieve it in form of blocks where you just take the number of alphabets and map them into a number of blocks. I'm not going to go through that. Okay, we have ones which use the fixed length codes, and that is the common type of source encoders, because normally we don't want one bit to be represented by 0, another bit to be represented by 2 bits, another bit to be represented by 3 bits. So we tend to have that. Then we have the variable code length, the example of which we are going to look at this, like the Huffman source coding theorem, which we are going to be looking at shortly. Okay. And then we have the distinct non-singular codes. So please go through and look at the different types of codes. Okay. Now in your Simon Heck's, basically the codes we are going to be looking at are these the prefix codes and these ones of variable. Those are the ones that we are basically going to look at. Now this looks very abstract until we start looking at the actual example. So let's look at this example. Okay. And in your notes, I'm going to give you about 5 minutes. 5 minutes are too many. I'm going to give you 1 minute for each. So this is an example which I picked from Simon Heck's. And this is how it looks like. Okay. This is a prefix code. What do they mean by prefix code? A prefix code is a code which is any sequence consisting of an initial part of the code word is called the prefix. But what does that mean? It means that the code in which no code word is a prefix of the other. Okay. Pre means something which comes before. So if you're going to represent any as a prefix code, you must make sure that the previous letter, the previous code word that comes before does not introduce any form of ambiguity. Okay, and we're just going to look at this and determine which of these, because these are just abstract generated code words to explain what they are trying to say. Okay, and we shall just identify what that basically means from this code word. So the decoding can be done as soon as the code word. So if it's a prefix code, it means that you can, as soon as you look at the code word, you can say, okay, this is what was transmitted, and this is not what was transmitted. Okay, and it normally gives the minimum code length. So let's look at these 3 examples which they have given to represent this information. And shortly, I will ask you to actually calculate each of this information. Okay, so let's look at code 1. They're saying 0 is represented by 0, 1 is represented by, sorry, S0, 0, S1, 1, S2, 0, 0, and S3, 0, 0. Now I want you to help me to find out whether this is a prefix code 1. What happens if you have 0, 0? If you have 0, 0, there's a possibility that you transmitted S0 twice. So if you look at that, if you look at S0 and S2, there's a bit of ambiguity. Okay, it is possible if you receive 0, 0, you could have transmitted S0 twice, or you could have transmitted S2 once. So there's a form of ambiguity. The same applies to S1 and S3. Okay, let's look at this other code. If you have S0, you transmitted a 0. If you have S1, you transmitted a 1, 0. If you have S2, you transmitted a 1, 1, 0. And you have S3, you transmitted a 1, 1. Okay, just take note of that. So if you receive a 0, you straight away know that I transmitted S0. If you receive a 1, 0, you straight away know I transmitted S1, and so on and so forth. But look at this one. If you transmit code number 3, S0 is 0, S1 is 0, 1. And now look at S2. S2 is 0, 1, 1. There's a problem here. Okay. Why? Can someone identify the problem? Can someone identify the problem in in code 3? Can someone identify the problem in code 3? Look at S2 and S1. Look at S2 and S1. We can see that S1 is a prefix of S2. S1 is a prefix of S2. So already there is a problem. Okay. So it means that this code number 3 is not a prefix. Code number 1 and code number 3 are not prefix codes. Why? Because they introduced a bit of ambiguity in the terms of coding. So for instance, S2 here, it has a prefix of 0, 1. Okay. So but anyway, before we continue, can you tell us can you calculate the information? What is the information contained in S1, S2, S0, S1, S2, and S3? Can someone post in the chat room? Calculate it quickly before we move, because we're going to use it shortly. It's very important. So what is information for S0? So someone calculate one for S0. Let me, if I have no volunteers, I'm going to pick from you. If I have no, Namata calculate the information for S0. Okay. Namudu Maria Christine calculate the information for S1. Paul Aineviona calculate the information for S2. Okay. And let's see someone else who has not been participating. Kasim, calculate the information for S3. We are waiting for your answers. Post the answers in the chat room. We are giving you 1 minute. Quickly. We don't have a lot of time. We don't have a lot of time, and we must finish this part of whatever so that we can finish it again. So what are the answers? So please put S1, say S1 is this one. Okay, so I can see Isaac is saying, no, there's no minus. There's no minus. You don't have minuses. No, we cannot get S3. S3 is equal to 3. No, that's not true. Okay, I can see, I think some people are reading ahead of us. Okay, which is good. I can see people are already reading ahead of us, which is good. I can see people are reading ahead of us, which is good. So if you look at this, okay, because we say that the prefix code for this particular example, okay, is given by this. So the information contained in S0 is definitely 1. The information contained in S1 is 2. The information contained in S2 is 3. And the information contained in S3 is 3. 3 bits, 3 bits, 2 bits, and 1 bit. You can, I think the people who have answered here are very, very clever, which is good, or they are at least reading ahead, or they are reading as we continue this lecture. Okay, because I also got this from, but the opposite is if you go through the actual calculations. If you go through the actual calculation, you should be able to discover that this is 1, this is 2, this is 3, this is 3. What about the entropy? What is the entropy? What is the entropy of this source? What is the entropy of this source? Who's going to answer this? Can you calculate for us the entropy for that source? What is the entropy for that source? Quickly. Who has the answer? Post it in the chat too. Post your answers in the chat room. Quickly. I'm waiting. And I would expect that the same people who gave me the answers. So the entropy, remember, we say the entropy is what? It's the probability times the information. The probability times the information. So what is 0.5 times 1? So basically it is 0.5 times 1, 0.25 times 2, 0.125 times 3, and 0.125 times 3. So that plus that plus that plus that. So Kasim is saying 1.75. I hope it is true. Okay, let's see. It is 0.5 plus 0.25 plus 0.25. No, not 25. 0.1. This is what? This is 0. This is times 3. Okay, plus this times 3. Anyway, let's assume that Kasim is correct because we don't really have a lot of time. Let's assume that Kasim is correct. So if you add this times 1 plus this times 2 plus this times 3 plus this times 3, let's assume that Kasim is correct and it's 1.75. Okay. So these are some of the conditions that meet the prefix that you should, for you to have a prefix code. So that was the first condition. The second condition, the other conditions, this is what it's supposed to be. It's supposed to be uniquely decodable. Okay. It's supposed to follow the Kraft-Macmillan inequality. Okay. This is what the Kraft-Macmillan inequality have. It should be falling within this boundary. Okay. And we know, of course, we know that this gives us the summation of our probability. And then this gives us the average code length. Okay, you can go and try to see if this is correct. So we don't have much time, but I want to leave to, though I would have wanted to go through Huffman coding, but maybe we'll go through Huffman coding together on Friday. So I want you to look at this example, and I want to leave you with this example. Okay, please go back and go through this example, and then when we shall start with this one, forgetting. So this is the example I want you to look through and go through. Okay, and then determine the average code length of a run and the corresponding efficiency, corresponding effective information rate for this source when the scanner is done that. And then lastly, calculate the coding efficiency. Okay, any questions before we break off? Any questions? Any questions? Now, Abapo, before you were in, for those people who have come late, we say that we're going to have our first cut on Wednesday, the 1st of December, and it's going to be physical. We're going to have our first cut on Wednesday, the 1st of December, and it's going to be physical. Okay, so please inform your friends, and it's going to cover everything that we have covered. In other words, it's going to cover signals, probability, analog to digital conversion, and also what we are covering now. Okay, that's what we are going to do. On the 1st of December, we are going to have our first cut. What else did we say? Oh, remind me, our class representative, what was who? Let me see, who was our class representative that we chose? What else did we say? Let me try to remember our class representative.
Yes.
Yes, what else did we say? Manuel?
Yes, I talked of having a class on Friday if possible. Then you will give us a reply.
Yes. Yes, so Friday 8 to 10 tentatively, I will communicate the link, or I will communicate a possible change. Because I've not yet got the link, unfortunately. I got the information this week, but I did not book the link. So I will need to make sure that the link is there. Yes, yeah. So that's what we shared. So otherwise, all the best. Make sure that you are safe and you and your families are safe. Please do not be involved in those terrorism activities that are happening, and try to remain positive. Because if you don't have hope, hope is what keeps us moving on. So make sure that you remain hopeful and try to be vigilant and make sure that you are safe. Yeah. Otherwise, all the best. Since you don't have any questions, I think we can stop here. There are only 6 minutes left to the top of the hour. So we shall stop here. Okay. Yes, someone else complained that the recordings were not being opened because there were issues of license, but that has been rectified. Try and see if you can see the recordings. If you are not, let me know, because then we can resend them, because I think that issue of the license has been sorted out. Okay, all the best otherwise. Bye. Yes, Nathan.